Good morning, everyone. Welcome to the Best Practices for Making the Most Accurate Radar Pulse Measurement web seminar. My name is Hua. I'm the Marketing Product Planner in charge of the power measurement solution that will be illustrated today. I'll be your host and also your question manager. I'm also pleased to introduce my colleague, Agilent Lim, who is the Product Marketing Engineer and also our presenter for today. Agilent Technologies is the market leader in RF and microwave power measurement solution. We offer the widest range of solutions from portable USB to bench, from peak to average, from 9 kHz up to 110 GHz, and from as low as -70 dBm to 44 dBm. This enables our customers to work on a wide variety of applications, whether it is in aerospace, defense, or wireless communications. As a long-time manufacturer of power measurement tools, Agilent has invaluable knowledge to share with you on how to make the most optimal radar measurement. So today our webcast goal is to provide you with the various tips to make the fastest and most accurate radar measurement. The topic that we are going to cover include the overview of IEEE Standard for power measurement, some tips on how to achieve accurate and consistent rise and fall time measurement, how to capture RF pulse with noisy spikes, how to maximize your equipment dynamic range, and lastly, how to maximize your measurement speed. Please be reminded that this is a recorded event, so this will allow you to review it later on or to share with your colleagues. The webcast will be a listen-only mode. Therefore, your phones will be muted to minimize any background noise for everyone's convenience. We will have a Q&A session at the end of this presentation. This will be anonymous, so feel free to submit your question at any time during the webcast using the chat area, and we will do our best to answer them within the time given. We are also offering the opportunity for you to provide us with your feedback by answering a short survey at the end of the webcast. So now, without further delay, I'll let my colleague Adeline to guide you through this exciting presentation. Adeline, I'm now passing over the session to you.
Thank you, Sukhwa. Hi, everyone. My name is Agilent Lim, and I'm the Product Marketing Engineer for Power Meter and Power Sensor in Agilent Technologies. Today, I'll be presenting this paper titled Best Practices for Making the Most Accurate Radar Pulse Measurements. This presentation will take roughly about 40 minutes so that we can have time to take some questions from the audience. My colleague, Sukhwa, will be the question and answer manager for today's webcast. Let's get things started by looking at the agenda or overall contents for today's presentation. An overview of the presentation content is shown over here. Firstly, I will go through the standards and definitions for pulse power and pulse parameter measurements. Then, I will share how to achieve accurate and consistent rise and fall time measurement. Next, you will learn how to capture RF signals with noisy spikes and measure small signals below -25 dBm. And then, you will see what can be done to improve the test time in your day-to-day tasks. And finally, before we end this presentation, I think it is good if we can spend some time to talk about the new Agilent U2020 X-Series USB peak and average power sensor. We will highlight the great features and performance of these instruments. Now, let's get started on the standards and definitions. Power envelope and RF pulse is governed by the IEEE Standard 181-2011. This standard defines the definitions and algorithm for pulse power and pulse parameter measurements. There are approximately 100 terms in this standard. Some of the most commonly known terms are transition duration, pulse duration, peak power, pulse amplitude, and duty factor. A common definition and algorithm are important to ensure that equipment from all manufacturers are returning accurate and consistent results. All Agilent power meters and sensors are referenced to this standard for measurement computation in order to ensure measurement consistency. A very common question from power meter and sensor users is as follows. How do we achieve an accurate and consistent rise and fall time, or also known as a transition duration for measurements? Well, first of all, you need to understand and use the right power reference levels. The standard 10%, 50%, and 90% levels are commonly used to define rise and fall time, that is a transition duration measurement, and pulse width, or the pulse duration. For instance, rise time is defined as a time difference between 10% and 90% reference level of the same transition. However, occasionally, you may hear that 1%, 25%, and 81% are used as the reference levels. This is because most of the timing in radar system is derived in the voltage domain for the time between control pulses. When we measure the RF signal that is modulated by these voltages, the 10%, 50%, and 90% in the voltage domain must be scaled accordingly, and this is mapped to 1%, 25%, and 81% in the power domain, since power is proportionate to the voltage grade. It is also common to look at the power waveform with dB scale. Here, at the 10%, 50%, and 90% levels can be calculated and mapped to the -10, -3, and -0.5 dB respectively, while 10%, 25%, and 81% will be mapped to the -20, -6, and -9 dB. Seeing these numbers expressed in dB makes it apparent that when we want to ensure a consistent and accurate transition duration, that is what we call the rise and fall time measurement, the power in the pulse must be at least 20 dB above the instrument's noise floor in order for it to compute the 1% to 81% transition duration measurement accurately. The IEEE Standard also defines the algorithm that can be used to determine the right power reference levels. First of all, we generate a histogram based on the pulse top signal here. Then, the mode of this histogram will be used by the power meter as the 100% reference level. The same applies to the pulse base, whereby another histogram is being generated. The mode of the histogram will be the 0% reference level. Once the 0% and the 100% reference levels are determined, it is just a matter of mathematical calculation to get the rest of the reference levels. Most power meter and sensors will allow you to adjust the reference levels that will be used to perform automatic rise and fall time, as well as pulse width measurement. The sample screen shown here is our N1918A Power Analysis Manager software that can be used with our new Agilent peak power USB sensor to adjust the reference levels accordingly. Let's take a case study of the rise time measurement of a 10 dBm signal from Agilent signal source using the Agilent new peak power USB sensor. The table here shows the rise measurements results based on different capture size for the peak sensor from 30 nanoseconds per division up to 500 nanoseconds per division, while the trace start time is fixed at -100 nanoseconds. Notice that the rise time results are different. The rise time measurement starts to stabilize and consistent with 50 nanoseconds per division of time scale or capture size of 500 nanoseconds onwards. The reason for this will be explained in the next slide. This is the rising age of the pulse signal from the signal generator captured using the Agilent peak sensor. If you display the pulse signal using unit of dBm, it is hard to tell how much time before the signal reaches its 100% level as shown in this figure here. But if you change the time scale to unit of watts, it is easy to tell that the pulse signal from the signal generator only reaches its 100% level after 500 nanoseconds, as shown on the figure on the right. Therefore, if the capture size of the power meter is not set to big enough to capture the entire rising age till its 100% level, the rise time measurement will be lower and will not be as accurate. Hence, the rule of thumb here is to get accurate measurement is to set the time scale of the power meter to zoom into the rising age of the signal. Make sure that the time scale is long enough so that the pulse stop or the 100% reference level is fully captured. I hope by now you have a general understanding on how to obtain accurate and consistent rise and fall time measurement. Next, we will take a look at how to capture RF pulses with noisy spikes. This plot shows a typical well-behaved but noisy RF power signal having a leading rising age masked by a noisy spike. The noise spike at point X exceeds the trigger threshold, but immediately drops below the threshold. The first point at which the RF signal is completely above the trigger threshold is point Y. However, if the noise were to be filtered out, the actual trigger point will actually be shown here at point Z. Therefore, to get a more accurate trigger, hysteresis is introduced. Instead of having just a single trigger threshold, two thresholds are provided, one on each side of the actual desired trigger threshold, an upper threshold and a lower hysteresis threshold. For valid age detection, the RF signal must rise above the upper hysteresis threshold and not fall below the lower hysteresis threshold within a certain time period that is known as a qualification time. The qualification time should be large enough to reject noise, but small enough not to reject genuine pulses. With this technique, point Z here, as shown on the right figure, is the first point at which the RF signal has risen above the upper hysteresis threshold and not falling again below the lower hysteresis threshold between the qualification time. Therefore, the rising age is detected as point Z, which is the accurate and desired trigger point. This method is well known and is widespread use in oscilloscope and power meters. However, hysteresis for noise rejection, if applied to the waveform as shown here, could cause a whole burst to be missed, as the signal always drops below the lower hysteresis threshold within the qualification time. Qualification time can be reduced to allow the front edge of the pulse to be detected, but this will also result in the 6 small pulses to be detected instead of one larger one. Therefore, Another technique of trigger hold-off is used to prevent problems arising from multi-triggering by suppressing triggers for a time after the first detection. It is recommended that the trigger hold-off time be set for a duration longer than the signal burst. With this setting, the power meter will be able to capture complex digital modulated signals such as OFDM pulses. A lot of times, you may face the problem that your power meter is not having sufficient dynamic range to meet your measurement needs. So, in the next section, I am going to share about how to maximize the dynamic range of your power meter and measure pulse signal at negative 25 dBm or below. Let's take a case study of measuring a very low power signal from signal generator with the new Agilent U2020 X series USB peak and average sensor. You may face the problem whereby there is an unstable trigger due to the signals that are too close to the noise floor. By default, most of the power meters are using internal trigger as the trigger source. However, internal trigger will not work as well if the RF signal is too close to the noise floor. In this case, users are advisable to use external triggering as it allows users to synchronize the measurement capture with an external trigger input signal. This will enable more accurate triggering of small signal close to the signal noise floor. The second tip here is to make use of the video bandwidth setting. These figures show the comparison of the power measurements with different video bandwidth settings, that is 30 MHz and 5 MHz, and their corresponding captured RF envelope. The pulse power is set to negative 25 dBm, while external triggering is used to capture the signal. Note that the smaller the video bandwidth, the smaller the noise as riding on the RF pulses. This is due to the high frequency spectrum that constitutes that noise signals are removed, therefore leaving a smoother trace response. However, do note that when the video bandwidth setting is reduced, the power meter system rise time will increase. This will result in a larger minimum rise of fall time measurement. You may feel that the previous trace results is still not good enough and it is still quite noisy. You can further eliminate the noise by applying video averaging setting. The figure shows the same negative 25 dBm signal captured using the video averaging setting of 64. Note that the noise has been removed and now you can see a very clean signal. You can measure even down to lower than negative 25 dBm of peak signal with the combination of external triggering by lowering down the video bandwidth and applying sufficient video averaging. Next, let's talk about what can be done to improve measurement test time. There are three possibilities to measure speed settings in most Agilent power meters and sensors. That is the normal, double, and fast mode. These settings can be set using the measure rate command. The default speed setting is normal. Fast mode provides the fastest measurement speed, but it has some limitations such as the averaging, limits and ratio, or we call it the difference mathematical functions, are disabled. In both normal and double mode, full instrument functionality is available. The difference between double and normal mode is due to the time constant for the internal resistant capacitance filter. A smaller time constant will cause more noise but provide faster measurement speed. The power meter returns a measurement upon receiving a query. To obtain each and every measurement, users need to send a query command, then take the measurement. When taking a large amount of readings, let's say 1,000, the user must send 1,000 queries and read the results 1,000 times. This method results in a longer test time because of the overhead of the programming and power meter operation itself. This overhead can be greatly reduced by accumulating measurements in the power meter buffer mode by sending the measurements all out in one read operation by the controller. To get a faster measurement speed, the skippy command must be set to return multiple measurements for each fetch command. This is called the buffer mode, whereby the measurements are accumulated before retrieving all the measurements in one read. The command trigger count is used to set the size of the power meter's output buffer. The default setting for the trigger count is 1. To get fastest measurement speed, trigger count must be set to return multiple measurements for each fetch command. Buffer mode is useful if users want to retrieve multiple readings at once for fastest measurement speed with the combination of fast mode setting. However, in fast mode, as explained previously, there is no average count applied and may produce less accurate measurement. If user only needs to retrieve one measurement at a time, then the non-buffer mode is the best solution with the trade-off of measurement speed. Modern power meter also allows you to capture 10 consecutive pulses simultaneously so that you could analyze pulse-to-pulse changes in terms of power levels or pulse shape. For example, as shown here on this graph, you could measure pulse width, rise and fall time of every single pulse here for pulse-to-pulse variation. Simply insert a numerical number in your skippy command, as shown in the table here, to indicate which pulse you would like to measure. This feature ensures that you are measuring every single pulse without missing out any of them. Another useful tip to improve your test time is to make use of presets, which is predefined measurement setup. This helps to reduce the setup time to obtain the first measurement. The commonly available presets are GSM, radar, DME, AH, wireless LAN, WiMAX, CDMA, and so forth. You just need to hit one or two buttons on your power meter and it will be set up automatically to make measurements that you need. Now, just to recap on the various topics that I've shared earlier on how to make accurate radar pulse measurements. First, you have learned that you can achieve accurate and consistent rise and fall time by applying the right reference levels and zooming in on the rising and falling edge of the signal to be captured to ensure that you have the entire pulse top captured. Secondly, trigger hysteresis and trigger hold-off function can be used to capture RF pulse with noise spikes. The third topic covered today is how to capture and measure low output power for negative 25 dBm and below. To do this, you need to apply external triggering, lowering the video bandwidth and increase the video averaging until the desired result is shown. Lastly, we talk about test time improvement. You learn that you can increase your throughput significantly by using the fast and buffer mode, making use of the multi-pulse function and also the built-in presets that you have available in your power meters. Now, I would like to just switch gear a little bit and share with you the Agilent power meter and sensor series for RF and microwave measurements. This is a series of power meter offerings from Agilent, ranging from low-cost handheld, USB version for field applications, benchtop power meters from manufacturing applications, faceless LXI power meter for system integrators, and high-performance peak power analyzer with 150 MHz video bandwidth for R&D applications. The latest addition that we have to the power meter family is the USB peak and average sensor. This peak USB sensor was officially launched in June this year. Our new USB peak power sensor offers the fastest measurement speed, wide peak dynamic range, best-in-class linearity, and it is easy to use. With our internal zeroing and calibration feature, this USB sensor simplifies your test setup. Unlike competitive offerings, this Agilent USB sensor have integrated internal and external triggering and do not require an external power supply. The USB U2020X series average and peak power sensor comes in two models, from 50 MHz to 18 GHz and 40 GHz. We have the fastest sampling time and measurement speed of any USB sensor. Our peak power dynamic range is superior and best-in-class linearity. Our true plug-and-play capability makes this product easy to use and comes with internal zeroing and calibration, which means you do not need to remove the sensor for external calibration. This product is bundled with the N1918A Power Analysis Manager software at no additional cost. This is easy to set up even for more complex measurements and can be used in aerospace and defense, wireless, and general purpose industry. Apart from the selection guide available on the Agilent website, you can also download the mobile selection guide application to be used on your iPhone or iPad. This is available free of charge in App Store by searching the term Agilent. This great tool will help you to select and view available options of Agilent power meter and sensors easily and conveniently with a touch on your mobile devices. To obtain the application note for this webcast, do visit our Power Measurement hints and tips webpage listed here. That is www.agilent.com/find/RF-power-tips. You can also visit the respective websites for more information on Agilent power meter and sensors, and in particular, our new U2020 X series USB peak and average power sensor. We have come to the end of the presentation. Thank you for your time and participation in this webcast. I will pass this back to our host and question manager, Suk-Hwa.
Thank you very much, Adeline, for your great presentation. It's now time for question and answers. For those who haven't done it yet, please use the Q&A box as provided in the WebEx tool to submit your question. And this is anonymous.
Okay, the first question that we have, what is the accuracy of rise time measurement for the new U2020 USB peak power sensor?
Thanks, Adeline. That's a great question. So the answer to this is that the accuracy of the rise time measurement is actually a function of the sensor system rise time and also the signal under test rise time. And the equation is quite complicated, so I will not provide it over here, but you can actually find the formula in the sensor datasheet as you can download it on agilent.com website. There's also a graph that's showing the percentage of error that you can expect if your signal under test rise time is in the range of a nanosecond. For instance, if your signal rise time is, let's say, around 30 nanoseconds, then you can actually expect that the error to be less than 10% or even less. And the error become insignificant when your signal rise time is actually more than 90 nanoseconds.
Okay.
I hope that answers your question.
Okay.
So we have more time? Yeah.
Yeah, I think we have more questions. The next question we have, is the new U2020 X series sensor compatible with other Agilent instruments?
Yeah, that is a very popular question that comes to us. So the answer is yes. The new U2020 series sensor are actually now compatible with our Agilent handheld spectrum analyzer, the N93-4XC. And the compatibility with other instruments such as Fieldfox and network analyzer and signal source are coming soon. So you may look out for the news update from Agilent from time to time. So at the moment, it is compatible with the Agilent handheld spectrum analyzer, and more will be coming soon.
Okay. Let's see if we have more questions in the chat box. Which meter do you recommend if you like to measure a signal with a rise time in nanosecond range?
All right. To measure a signal with the rise time in a nanosecond range, we have a few solutions. One of them is the Agilent 8990 series peak power analyzer, which is the Agilent power measurement equipment with the best rise time performance of 5 nanoseconds. It is then followed by the P-series power meter and also the new X-series USB peak sensor. Both of them is actually having the rise time performance of around 13 nanoseconds, 13 nanoseconds. And there is actually a graph showing the percentage of error that you may expect if, let's say, your signal test rise time is in the nanosecond range in the datasheet of this power meter. That's a great question. Thank you for that.
Okay. The next question is, how do we request for USB, the USB peak sensor, a demo unit to try it out?
At the end of this session, you will, after you close the window, there'll be a message box pop up that asking you to fill up the evaluation form. And after you fill up the form, then we will actually contact you accordingly for the demo unit evaluation.
Okay. Thanks, Hua.
All right. I think we can bring this session to a close now, since we do not have any more questions. Please take a few seconds to complete the evaluation form that will pop up on your screen after you have closed this window. And we do appreciate your feedback. Thank you again for your attendance, and I wish you all a